Hello and welcome. In this video, we want to take a look at a certain type of vector field called a gradient field. Back in Calc 3, we learned the concept of a gradient, although at the time we didn't necessarily call it a vector field. What we did was we said, if we've got a function of two variables, well, in R2 it would be a function of two variables, right? You got two variables in, one variable out. We defined the gradient to be a vector where the first component of the gradient was the partial with respect to x and the second component was the partial with respect to y. Now, we said it's a vector, but it was a function of x and y. That is, each point in the plane could give you a different vector because you could plug it in and there were formulas that the partial with respect to x was not a constant, the partial with respect to y wasn't necessarily a constant, right? So you could get different outputs for the same input. You get different vector outputs for different inputs. So it was a vector field. Likewise, if you had a function of three variables, f of x, y, and z, then the gradient was a vector in three space, being the first component is partial with respect to x, the second component was partial with respect to y, and the third component is partial with respect to z. Again, each of those are functions of x, y, and z. So these gradients are actually vector fields. Okay, so the gradient of a function of several variables is a vector field, but not all vector fields are necessarily gradients of some function. And we will look at which ones are and which ones aren't over the next couple of sections of the book here. I want to give a definition here. A vector field is called conservative if it's a gradient field, essentially. It's called conservative if there exists a function, f of xy in R2 or f of xyz in R3, such that your vector field is in fact the gradient of this function. The function little f is often called the potential function for that gradient field. Here's an example of a vector field that is conservative, and I will show it's conservative by showing you that this function down here is the potential function for it. Now I want to point out that this vector field is the gravity vector field that we looked at in the previous video. That is, at each point xy, the vector points directly back at the origin, minus x minus y, and it's scaled so that the length of each vector is proportional to the reciprocal of the square of the distance from the origin. Okay. And here's my potential function here of the quantity x squared plus y squared raised to the minus a half power. So you could think of this as 1 over the square root of x squared plus y squared. And if I take the gradient of this, I take the gradient by first taking the partial with respect to x and then the partial with respect to y and making a vector out of that. Well, taking the partial with respect to x, the minus a half pops out in front. That exponent then drops to minus 3/2. Chain rule then says times the derivative of the inside, but I'm taking the partial derivative with respect to x, so the partial derivative of the inside there with respect to x is just 2x. The 2's cancel out, and I end up with that first component of v there. Likewise, if I took the partial with respect to y, it looks very much the same, except that the chain rule is taking the partial with respect to y on the inside, which now becomes a 2y. Again, the 2's cancel out, and I end up with that. So the gradient of this function, little f, is indeed the vector field that we started with. So that is a conservative vector field. I should point out this is conservative everywhere except for one point, because at the origin, the vector field isn't even defined. When you plug in 0, 0 for x and y, you've got to divide it by 0 here. So anywhere except the origin, this is conservative. Okay. Here's an example that is not conservative. And you might ask, how do I know it's not conservative? Well, that's what we're going to take a look at next. But one of the things I look at is I've got a pretty good idea of the geometry of what the gradient tells me, right? That back in Calc 3, I learned that the direction at each point, the direction that the gradient is pointing in is the direction that the potential function is moving up the fastest, right? So when I look at something like this that's got all these circles going around, it's like if I wanted to just keep walking uphill, right, I'd just always be walking in the direction that the gradient is pointing to, and I would just be walking around in circles. And it's like, how could a surface be you know, when you walk around in a circle, how could it be always going uphill? It's like, it's like, are we looking at an Escher painting where, you know, he's got that famous one of the waterfall where you got the waterfall going down and the river goes out, it goes back, it goes up, and then it's over the waterfall again. It's like, is that always going uphill if you're walking backwards in the water there? Yeah, so this couldn't be a gradient field just from just the geometry of it, but we'll prove it to you here down below as to why it's not conservative. And here's the theorem that we need. So let's pull this up here. If you have a vector field F, and we're going to specify the component functions now, that the first component of the vector field we're calling capital P of xy, and the second component is capital Q of xy. If it is a conservative vector field in R2, whose component functions, P and Q, are continuous, that have continuous partial derivatives, then the partial of P with respect to y is equal to the partial of Q with respect to x. So if it's conservative, I claim that these particular partial derivatives have to be equal to each other. Likewise, if your vector field is in R3, so my components are now P of xyz, Q of xyz, and R of xyz. Those are the x, y, and z components of my output here for this vector function, this vector field. I say, if this is conservative in R3, then there's three equalities here of partial derivatives. So the partial of P with respect to y is equal to the partial of Q with respect to x. Likewise, the partial of P with respect to z is equal to the partial of R with respect to x. And the partial of Q with respect to z is equal to the partial of R with respect to y. So if it's conservative, then these things are true. Notice it's not saying the other way. It's not saying if these things are true, then it's conservative. This is just a one direction theorem. And the proof here is essentially Colars theorem from Calc 3. And I'll remind you of Colars theorem. Colars theorem was saying that if you've got a function of several variables that has continuous second partial derivatives, then the mixed partials will be equal, right? If you take the partial with respect to x and then y, or with respect to y and then x, you get to the same place, right? And that works for a function of two variables or a function of three variables. It's that fxy equals fyx, right? That you take the partial in either order and you get to the same place. And so what we want to point out that to prove this theorem is we'll do it in 2D and then in 3D, but here's the 2D version of the proof. We're given that capital F is a conservative vector field. So there's a potential function. There is some function, little f of xy, so that the gradient of little f is equal to the vector field capital F. Okay. Well, remember, the gradient of little f is calculated by take the partial of little f with respect to x as the first component, take the partial of f with respect to y as your second component. So that now has to equal capital F, which is P comma Q, right? That was the x and y components of capital F. So this is telling me that the first component of the gradient, the first component of that vector field, the first component is P, has to equal to the first component of the gradient, which is partial of f with respect to x. Okay. Likewise, Q has to equal the partial of f with respect to y. So I've got these two things. Now, if I take this first equation and say take the partial derivative of both sides with respect to y, I get the partial of P with respect to y, and here I get the partial of f, first with respect to x, and then with respect to y, which we usually write as f sub xy. Okay. Likewise, over here, if I take the partial of q with respect to x and the partial of this with respect to x, so both sides, same thing here, partial of q with respect to x has to equal to the second partial f with first with respect to y and then with respect to x. But here's where Colars theorem comes in and says, hey, this mixed partial is equal to that mixed partial, and so the partial of p with respect to y has to equal the partial of q with respect to x, as we claimed in the statement of the theorem up here. Okay. Likewise, in R3, you would have that, of course, there's three components to the vector field P, Q, and R, and there's three components to the gradient of F, partial with respect to x, partial with respect to y, partial with respect to z, right? And so p has to equal the partial of f with respect to x, q has to equal the partial of f with respect to y, and r has to equal the partial of f with respect to z. And we get the same conclusion by taking mixed second partials. So for instance, this first one, I would take the partial of both sides with respect to y, because this is already the partial. So the partial of p with respect to y would be the partial of f with respect to x and then y. Likewise here, if I took the partial with respect to x, well, this would be the same thing as what was up above, right? So throw an r into the mix. Let's go back here. Take the partial of p with respect to z. So then the partial on the right-hand side would be f sub xz. Now on this one right here, take the partial with respect to x. That would be partial of r with respect to x. And here, this would be f sub zx. So f sub zx equals f sub xz. So the partial of p with respect to z should equal the partial of r with respect to x, which was this one right here, right? And likewise, you just do those appropriate partial derivatives to get those equal to each other. And it all comes down to Colars theorem. Since we assumed that f was a conservative vector field with partial derivatives of its component functions that are continuous, then we have Colars theorem applying, and we have the conclusion that we want. Okay. So how did I know that this vector field up here was not conservative? We'll take a look. Right. Here we go. An example. There's the vector field I had. The first component was, so this is v of xy is equal to negative y for the first component, x for the second component. It's not conservative because if I take the partial of this first one with respect to y, right, so p is minus y and q is equal to x. Partial of p with respect to y is minus 1, but the partial of q with respect to x is positive 1. Minus 1 is not equal to positive 1. So this could not possibly be conservative. If it was conservative, those two things should be equal to each other, but they're not, so it isn't. Right? This is the way this theorem works. It's not used for proving that something is conservative. It's used for something to prove that something is not conservative. If you can show that those partial derivatives are not equal, then it's not conservative. If you can show that those partial derivatives are equal, then it might be conservative, but there's other things that come into play, which we will look at in subsequent sections of the book here. Right? So there you go. This is a negative theorem only. That is, like, if you want to prove something is not conservative, then you can show that these partial derivatives are not equal. If you want to show that something is conservative, at this point of the game, what you have to do is you have to find a potential function whose gradient is equal to the vector field that you think is conservative. Okay, so there you go. Gradient fields as vector fields.